All right, I decided to shave my head, everyone. Hair, it's too much. It was growing it out. I tried dyeing it, and it didn't fit me. I decided to shave my head. That's kind of who I am. So this next section is something honestly really special to me. I think log scales are maybe the most important things over here. It's a very nice thing. So anyway, let's look at something. We're going to look at a table, and it shows a list of common sounds and their intensity level. So the softest sound with regular hearing that a human can hear has this intensity level in watts per meter squared. Normal breathing, okay, is a little louder. Whispering is a little louder. Rainfall, a little louder, a little louder. Okay, a lot louder. Handgun is going to mess your ears up. Okay. But these numbers are kind of silly. What if I told you to plot these? Plot these numbers on a number line. You'd say, okay, well, have a number line here. Let's have the smallest number here. Have the biggest number here. That's 100,000. We could split this up into 5 or like 10. Yeah, let's split this up into 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Pretend. Okay, let's make this a little better. 10. So again, this is 20,000. This is 50,000, right? This is 80,000. All right, let's plot these. Okay, well, softest sound with regular hearing is right here. And then normal breathing is right here. And then whispering is right here. And then rainfall is right here and right here and right here. And airplane taking off is right here. Okay, and a handgun's right here. This is useless. Okay. These numbers are basically growing exponentially. All these different numbers are growing exponentially, right? This is 10 times as loud, 10 times as loud, 10 times as loud, 10 times as loud. Oh, sorry. This one was 100 times as loud. And then 10,000 times as loud. And then again, 10 times as loud. This is growing exponentially. If you have data that's growing exponentially, we can't graph that really. We've done this before, right? You said, Melon, what are you talking? Jason, what are you talking about? You can graph exponentials, but you can't really graph an exponential function very well, right? The only thing you can see anything is like around here, but then it's way too close to 0, and then it goes off the graph. Okay? Exponential functions are notoriously hard to graph well. You can only see the behavior in a small region, and everything else is either 0 or too big. That's what log scales are all about. Okay? So, there's something you may have heard of before called a decibel. And that's essentially a logarithm with a couple of other adjustments. That's essentially a logarithm of the sound intensity. And decibels are a much better way of talking about loudness. And that's why when we do talk about loudness, we talk about decibels. Okay, much easier to talk about. So if a decibel level increases by 10, that means 10 times as loud, because it's on a logarithmic scale. This 10 times as loud. All right. This, it's not 30 times as loud. It's 10 times 10 times 10. That's 1,000 times as loud. All right. And that's what's going on here. Oh, I said 100 over here. I meant 1,000. And that's where we're going right here. So decibels are essentially things on log scales that we've already been using them. Let's formalize this a little bit more. Okay. So decibels are an example of a logarithmic scale. And on logarithmic scales, we don't graph the quantity itself. We graph the logarithm of the quantity. So instead of an x value, we plot capital X. Capital X is going to be the logarithm of that data value. Okay. So sometimes you'll see written as, here are our x's, our little x's. Capital X would be like 7 here, right? What's the common log of 10 to the 7th? It's 7. This would be 6. This would be 5 for capital X, and so on. And these are kind of two ways of looking at these graphs. You can either look at little x's that are written like this, or big x's that are the logarithm, the common log, usually, of those little x's. So we can see a point P is over here, somewhere between 10 to the negative first and 10 to the negative second. You can see the A values over here, and so on. This is much easier to read than if we graphed this on a linear scale. If we graphed this on a linear scale, we'd have the same kind of thing of a bunch of points near 0 that you can't really see, and then a much bigger point. So let's use a log scale a little bit. What's the value? Let's part A. What's the value of point A? Well, we know the value of point A, it's 10 to the first power. That's just, excuse me, that's just 10. All right. What's the logarithm, the common log of this value? Well, capital X will be the common log of little x. The value, the common log of 10, is just 1. Don't believe me? Plug it into your calculator. Common log is log base 10. They cancel each other out. We're just left with the exponent, which is a 1. All right, and so you can see that here. Value on top, the logarithm of the value on the bottom. So try to do more of these on your own if you want. Pause the video, try to do the other letters the same way that we did. What's the value of B? 10 squared. That's 100. What's the log of this value? Capital X in this case. We the log of 100. Common log cancels out with the exponential function. We're just left with that exponent of 2. Capital X is 2. Letter D. What's the value of P? That one's a little harder to see. It looks like it's between 1/10 and 100th, but it's not actually right in the middle. Because this is a logarithmic scale. It's not linear, so it's not halfway between these. But what we can do is, let's go backwards. I know the logarithm of that value, right? Capital X is linear. It's increasing by 1 every time. Little x is not linear, it's exponential. It's not growing by 1, it's growing by a factor of 10. Getting multiplied by 10, little x is exponential growth. So we do know big P is at capital X equals negative 1.5. So we know the log of that value is negative 1.5. And remember, that's the log of its actual value. So how do we find its actual value? We need to solve this logarithmic equation. Whoa! 5.2 coming right back at us, all right? So how do we solve this equation? We convert it to exponential form. Remember, this is the common log, log base 10. The base of the logarithm is the base of the exponential function. The input of the logarithm is the output of the exponential function. The output of the logarithm is the input of the exponential function. Oops. The exponential function's over here. I got very worried there for a second. And we can plug this in with a calculator. So the value of point B, that's going to be 10 raised to the negative 1.5 power, which is about 0.0316. So it's not halfway between these 2 points. It's halfway, the logarithm is halfway between the logarithm of those 2 points. The actual value is about 3/100ths. So sometimes it can be a little tricky to read these, but you can see much more information on a log scale than again, you could on a linear scale. Linear scale's terrible. You can't see anything on a linear scale. Everything's clustered together, and they got something that's really big that screws up the frame. Okay. Place a point S with a value of 6,000 on this log scale. So where is 6,000? Well, this is 10 cubed, that's 1,000. 10 to the fourth, that's 10,000. The 6,000 somewhere between there. But don't write this down. It's not right here. Oh, sorry. It's all right. You wouldn't have thought it's right there either. It's not right here is what I was trying to say. Okay. Because it's not a linear scale. We have to actually find out, if my computer doesn't freeze, we have to actually find out what is capital X? What is the logarithm of 6,000? And then we can plot capital X. Capital X is the common log of little x. And our data value, our little x, is 6,000. What is the log of 6,000? The common log of 6,000? I don't know. About 3.8. We don't need very much precision here because we're just graphing it. So we're going to graph it not 60% of the way between 3 and 4, but 3.8. So 80% of the way between these two data values. It actually does go much further. S is at a value of 3.8 on our log scale. Okay, and that's how we can use log scale. So watch out for this. They can be a little tricky, but they're so useful. And we'll talk about more usefulness in the next video.